So my name is Xavier Bocherel. I work from Johnson Matthey and based in the UK. So one of the industrial partners in the HIGFLY project and looking at some of the catalyst development. So we've start first session of this afternoon with Dr. Arjan Smit. So Arjan has been at TNO for 15 years, I believe, focusing on the development of this biorefinery concept that is now known as the Fabiola process. First focusing on the technology development, but more recently looking at the demonstration and commercialization of this process. So, but I'm sure Arjan will explain all of that much better than I can do in the next 25 minutes. Thank you.
Okay, thank you. And yeah, thank you for inviting me for this talk about Fabiola Biorefinery, the feedstock flexible biorefinery for bio-based building blocks. As you can see, it's in Biorizon format. So Biorizon is a collaboration between TNO and Vito on bioaromatics. And let's say partially the further development of the Fabiola process and its commercialization is supported within Biorizon, so hence the format. So you all know about the bio-based material transition, and basically for the biomass part, converting biomass to green building blocks, and the conversion and application in bio-based products, chemicals, and fuels. And why do we do that? Of course, to mitigate climate change and to progress towards a sustainable society. But also in recent years, it has become more apparent that there is an increased geostrategic risk, and overall it's a good idea to become less resource dependent in Europe, and also biomass can play an important role there. So we are active in the biorefinery technology development, and basically three things are for us very important. Firstly is to develop a biorefinery technology which is really cost effective. That is what is needed to, oh, whoops. Thank you for this. So cost effectiveness. Cost effectiveness is really important, otherwise we get nowhere. And the second thing is a good connection to sustainable feedstock supply chain. So that means feedstock flexibility for the biorefinery. So two, feedstock flexibility, and three is producing high quality building blocks for bio-based applications. So these three things are our main target. If we look at targets in the Netherlands, in Europe, if we just take a bit of a selection, there's a lot of new houses that need to be built in the Netherlands, and we aim in 2030 to have 30% of all building materials to be bio-based. And among others, we want to have a 50% reduction in, let's say, fossil-based primary resource use in 2030. And in Europe, it's the same story. So we want to have a 25% reduction in, or we want to have 25% bio-based chemicals and materials in the chemical industry by 2030. And we want to have a, now I have to guess a bit, 50% reduction. Let's say, given these aims, it's not my field of expertise, but I'm really wondering if politicians know the sheer size of the amounts of biomass and green building blocks that are needed in 2030 to realize these targets. So the effort is enormous. And let's say what we see, especially over the last year, is that there is more and more of a consensus, especially in the Netherlands, that progress is too slow. And with that in head, we come with the solution, Fabiola biorefining. And so what we are, our process is now validated at the pilot scale, and we're exploring a route towards a Fabiola demo. And what we are thinking about is a demonstration plant, which is between 100 and 1,000 tons of biomass per year. And let's say, as a very rough estimate, the investment is relatively high, so it's 20 to 40 million euro. And in the demo, we aim to convert a variety of different sustainable biomass residues via Fabiola biorefining to produce cellulose fibers, sugars and furanics, and lignin. with potentially an overall theme to go towards bio-based construction and insulation materials. So producing these materials, but also using bio-based adhesives and resins and coatings, and also partly directing the lignin to, for example, insulation foams. And the advantage on this topic is that, especially in the Netherlands, there's a lot of traction in the construction sector to go bio-based. And second, there is a large sustainability bonus because biomass carbon is used in materials that have a long use time. So basically, you're helping bio-based carbon sequestration. If we zoom a little bit in on the technology itself, then we have a very high feedstock flexibility, so we can process a lot of different feedstocks. And mainly that is because we do a pre-wash, pre-extraction to remove non-lignocellulose components. And if we take, for example, the average results of fractionation of roadside grass, beechwood, almond shells, and wheat straw, then first we have an aqueous pre-wash where we remove sand, metals, and stones, and the water-soluble organic extractives, and this is followed by an aqueous acetone extraction to remove more hydrophilic extractives. And removing such extractives has a very positive effect on the lignin purity. Otherwise, you would have, for example, fatty acids in the extractives pool that would co-precipitate with the lignin fraction. So we have this pre-extraction process, and then you enrich the feedstock in lignocellulose, and that really helps feedstock flexibility. Of course, it adds cost and energy demand, so this is something to keep in mind. And then for the average of these feedstocks, roughly 90% of feedstock weight is extracted. And basically, we see it as added value, so that we don't have it included in our, let's say the extraction process is included in our economic models, but not the value of the extractives. Then it goes into the fractionation step, so we have a relatively mild process at 140 degrees C using 50% acetone. And basically, we solubilize as much hemicellulose and lignin as we can, and we obtain a cellulose-enriched pulp, which is roughly 40% of feedstock weight, but also 40% of product revenue. And then we have a pulping liquor with in there the solubilized hemicellulose sugars, mostly, and the lignin. And we have a collaboration with Fraunhofer in Germany, and they have the Lignicep process, which is an advanced continuous process for lignin isolation, which is really cost effective. And you can isolate lignin in a full yield almost. And what is really remarkable about our process is the lignin is really high quality. So lighter color and high quality, and this is really needed to get the lignin to, let's say, high value polymer applications. And as you can see, the lignin is on average less, let's say less in amount, so 17% of feedstock weights, but it's 40% of product revenue. So for these type of processes, lignin is very important to valorize to higher end applications. After acetone recycle and lignin isolation, we have a hemicellulose hydrolysate, so this is an aqueous stream. And this contains mostly hemicellulose sugars, but also some cellulose sugars, which is 26% of feedstock weight and 20% of product revenue. And of course, we have some acetic acid, uronic acid, some protein. So basically, the hydrolysate is the sink of the process. Oops, that's not good. Okay, some highlights. So as I said, we have feedstock flexibility and excellent connection to feedstock supply chains, helping the sustainability part. We have a pre-wash to remove everything that can harm the further fractionation and downstream processing. And we are aiming for valorization of these non-lignocellulose compounds to, let's say, fine chemicals for a part, but also recovering what will be important in the future is recovery of the nutrients, so nitrate, phosphate, and try to get that recycled back to land. But this is not an active thing we are pursuing at the moment. Let's say feedstock flexibility also has the advantage that you have reduced biomass transport cost, but also reduced investment risk. So you're not dependent on a single feedstock, but you have this flexibility. Then for the fractionation process itself, so we have excellent scale-up results from lab to pilot scale using the facilities of Fraunhofer CBP in Germany. And we also now have a new process, so that's not a batch process, but that is smart coupling of an array of different batch reactors, which allows for semi-continuous counterflow processing, which is really beneficial for further improving, let's say, the yield and the quality, also for the lignin. And you don't need any washing steps for the pulp. So for, let's say, operational costs of this process, it has some large benefits. So this we have developed now at TRL3, and this also needs to be further scaled up. Because we use acetone instead of ethanol, we don't have ethylation of sugars, but also we have a very significant decrease in energy demand of around 50%. And we looked at corrosion and solvent loss, which are both okay. So these parts are, let's say, they can be important for further scale up. And if we then look at the output, we have very good numbers there. So let's say on average for different feedstocks, we have over 95% cellulose recovery, solid fibers. We have 90% hemicellulose recovery as solubilized sugars in the hydrolysate. We have 80% lignin recovery as a dry solid, and this lignin is then of, let's say, high quality, high purity, and we recover 80% of the extractives in the extracts. And because we have this three main product group, basically we have a zero waste refinery. And what is important is a good carbon transfer to the green building blocks, given these yields. Then, of course, there are many different types of add-on technologies. So for some applications, we can use the cellulose fibers, the lignin, and also even the sugars directly in some applications. But in the future, there is, of course, this very important role for, let's say, further conversion steps of these biorefinery fractions to a variety of different platform chemicals, fuels, and materials. And I cannot, given the time, go too deep into all these different routes, but these are for us the most important ones. So conversion of cellulose to sugars and go for fermentation. The enzymatic mechanical refining to nanocellulose, which is a very promising route. And especially also we developed a partial depolymerization process where we cleave the remaining ether linkages in the lignin to produce lignin oligomers. And what we have seen is that these smaller lignin oligomers are highly reactive in, for example, resins, coatings, and adhesives. So for polymer applications, going to lignin oligomers is a good idea. And we can do that, let's say, roughly in a 90 to 95% yield with a very mild reductive process. So we have a collaboration with Vito, who has a TRL7 depolymerization plant. So we're also aiming to scale up this route. And then also linking to, let's say, HIGFLY, we are looking then for conversion of the hemicellulose sugars to furanics, because that will remain a very important group of platform chemicals. And of course, we can go for fermentation to fuels and chemicals. And also what I wanted to note that, let's say, in this approach, if you would link this directly to the biorefinery, you get a certain flexibility because you don't have to try to convert all the hemicellulose sugars to furanics. But you can just do a milder treatment with a higher furfural yield, so less humin formation, and the sugars you have left, you can add it to the sugar pool for fermentation. So from biorefinery, it will be furanics and sugars. And it is very interesting to look at integration of these two processes. In the past, we were looking a lot at single value chains, so use of lignin in coatings and the use of cellulose in for example, textiles just recently. But slowly what we see, and also our interest, is shifting towards complex bio-based systems. And this brings a lot of opportunities. And I can give you one example, and that is the conversion of cellulose fibers to nanocellulose. For nanocellulose packaging, you can do functionalization, so to improve the nanocellulose packaging properties. But you can also add lignin oligomers, so to introduce fire resistance, fire retardancy, moisture resistance, antimicrobial effects. But also lignin has a very positive effect on the gas barrier properties of this packaging. And then from the third group, from the hemicellulose sugars, you can convert the sugars to furanics, and from furanics to plasticizers. We have a group in TNO who's very skilled at that. And you can add the plasticizer to the packaging. So this is one example where the three main building blocks are coming together in a more complex, tailored application. Then shortly, the applications. Let's say mainly what we are working on is a lot of TRL3 development, a lot of TRL3 to TRL5 development, and there are also a number of routes also still here that we are pursuing still. And a number of these routes are now more ready at TRL6. We want to have more applications validated at TRL 6-7, but then we always have like the chicken and the egg story. So basically you have to produce like 200 to 500 kilograms of lignin to do a very big, large-scale test, to validate these application routes to go to a demo, but you need a demo to produce 200 to 500 kilograms of lignin. So this is always a bit difficult. But our main focus is to produce chemicals and finally go to materials and then to construction and insulation materials and packaging and plastics. And we're not looking so much at fuels, but still, this is a very interesting part. So we have looked at bioethanol, and we had the HIGFLY project. And I think further strengthening on the fuel side remains interesting. Although for the demo, we are aiming for materials primarily. Then quickly the economics. So if we take our process and a 150 kiloton per year biorefinery, and we take some, let's say, rather conservative estimates. So for example, for the lignin price, €900 per ton. Lignin is often used as a phenol replacement, and phenol price is roughly over the last years between 1,000 and 2,000 euro per ton. So this price is on the lower end. And then the pulp price, which is very dependent on feedstocks and applications, but €600 per ton, and just the hemicellulose sugar market price. Then we come for this biorefinery at a total investment of a little bit over €100 million and a payout time of 7 years. So overall, we see strong biorefinery economics, but also we see in the models that there is a strong dependence on feedstock type, feedstock prices, energy cost, and what type of application you're steering your building blocks in. And so this dependence can go to the upside and to the downside. So this is not pure risk, but there is also an upside to this. And also from our semi-continuous process, this is not yet included in our economic models. And from there, we expect lower operational costs. So this is to be updated. Then one of our main targets now is to set up the business case for the Fabiola demo. And as we have a broad-based technology with a lot of choices, there is this very interesting web of different aspects that let's say, affect each other. I will not go into that in too much detail, but what we need to do is create a business case, a clear business case, reduce the complexity, and reduce the investment risk. And basically for the investment, what we are looking at is that we can go for a smaller demo, which does not have to be economically viable, or we go for a large demo with a larger investment and a larger investment risk, and then this demo needs to be economically viable. So we have these two options, and what we are, in addition, are looking at is our semi-continuous process. So because we use an array of reactors anyway, we can start with a simple feedstock and a few reactors, and then in a second step expand from batch-wise processing to semi-continuous processing, and in a third step add the pre-wash, pre-extraction, and go for sustainable biomass residues. So given our process design, we have the option to do it in stages. Whether that is a good idea, this is part of the let's say, our route towards establishing the business case and our talks with investors and a lot of other different stakeholders. Yeah, so takeaway messages. Basically, the material transition is going quite slow. One of the reasons is that a lack of legislation. This is also mentioned by industry a lot. And we have to compete with fully developed oil refineries, which is quite challenging. Second, what we do see is that the demand for high-quality building blocks is already increasing, and my personal feeling is that if there is some sort of legislation coming, there will be a huge shortage of building blocks, and it will take a very long time to have this production capacity from biorefineries implemented. So this will be interesting, and we want to be ready for that, and Fabiola is because Fabiola is a robust and viable technology option to produce these green building blocks. So, thank you. This is not everyone in the TNO team. This is these are the people who are working on the route towards a Fabiola demo. So not everyone is included. That's it.
Okay. Thank you, Arjan. We've got time for a few questions, if Axel?
One quick question. So one quick question. What is the weighted average cost of capital, and related to that, the debt to equity ratio you used for the calculation of profits?
Yes.
Is it like completely debt financing and 5% interest, or what is it?
Jan Wilco Dijkstra.
Oh,
he is the
guy.
expert.
Oh.
So, Jan Wilco, can you answer with the microphone, maybe?
Yeah, we have various economic indicators. I think for the one that they show, we use a 10% WACC based on. Yeah, it could also be 7. I don't remember by heart, but we assume a mix of debt and mix of equity and debt. Yeah.
Any more questions?
Sorry, slightly higher level question from me, but if for these sort of biorefinery concepts like yours, would you always envisage it as a sort of single integrated facility, or is there options for more sort of distributed networks for these sort of concepts? Do you think?
What do you mean exactly?
So is it always everything directly linked at a single site, or would you imagine more some elements of a distributed network where you could do certain processes in one place and some in another?
Yes.
I'm just thinking about how you then, because I guess biomass is not always easy to move around. What's the relationship? What's the best distribution, do you think?
It's a very good question, and let's say my personal view is that it is possible that in the future you'll get, like you have recycling centers now, you will have biomass valorization centers, and if you have like tomatoes or beet pulp or whatever, they have a too low lignocellulose content. So they will not go to biorefining, but they will go to a different technology. There is also a possibility that other technologies will be better for processing super clean wood, because they can make bioaromatics like Biocon or other technologies in Europe. So I think there will be, let's say, a biorefinery hub And there will be streams coming in, and there will be a selection going to different technologies. And let's say in this biorefinery hub, you will also have partly the downstream processing, but also the add-on technologies. And for example, an example I gave just before during lunch is that for the pre-wash, we are not going to use clean water. And for example, if you would have fermentation on site, and you have the fermentation wastewater, this is perfect to do the first pre-extraction. So our process is part of a whole, and I see the future more as like a hub and trying to integrate as much things as possible. Yeah. I hope that answers your question. Yeah.
Yes, my question is a bit related to these hubs. Which kind of feedstocks are you looking into to feed your biorefinery for building blocks? And do you consider only local feedstocks, or are you considering importing feedstocks?
That's both is possible. Again, I believe that clean wood will become too expensive. So let's say we are looking for the more sustainable biomass residues. That is one, given with the condition that they have sufficient lignocellulose content. And what we are looking at, it's very diverse. So let's say all types of agricultural residues, weeds, all kinds of straws, miscanthus, roadside grass, forestry residues, but also wood clippings, so with bark and wood. So this is really, let's say, a mixed intake where we can look at import or regional supply. What I think is the most interesting question is that you're not going to always process a mix. So let's say for cellulose fibers from straw or wood, you get very different fibers than, for example, for almond shells. So a nutshell is very different. So you cannot say, well, we are feedstock flexible and we can direct everything to nanocellulose packaging or construction panels, because some things are really feedstock related. And so personally, I'm interested in how this will work. So would you do campaigns? Do you separate some streams? And I think this is a good question for, let's say, any technology in the field at the moment.
Any more question? No? Quick one? Thank you.
I was just curious in the context of today with the SAF. So do you expect that you can be competitive in your process really to serve that biofuel market? Because that's a different cookie in terms of price levels and margins, etc.
Yeah, I think, let's say, for the first scale-ups of our process, also afterwards, let's say the hemicellulose sugar price will be market price. And that's what we are calculating with, and that will be, let's say, the business case in the economic model. And so the question is, like sustainable aviation fuels, can they use market price sugars? Yeah. And so basically it comes down to that, I think.
Okay. Thank you very much. Thank you. And thank you for keeping on time, besides the little technical
Yeah, was I on
issues.
time?
Yeah, pretty much. We keep the couple of minutes.